Assalamu alaikum. Ji beta. So today I'm going to solve Feb March 2022 paper 42, and this is the first paper as per the new syllabus. So there are few changes in the question paper. The first most important change is that the data booklet is not included anymore in the paper, right? But they've given you all the values you needed. For example, the table for IR or the table for proton NMR or carbon 13 NMR. So everything is in the paper. So I think it would save the time, right? And the second most important thing is the changes in the syllabus. So like there are few changes in the syllabus. For example, the relation between delta G and cell potential. So there is a question related to that part of the syllabus as well in this paper. But related to chiral chemistry, there is no question in this paper as well. All right, so let's just start with the question paper. So the first question is that iodine is found naturally in compounds in many different oxidation states. Iodine reacts with acidified hydrogen peroxide, right? Iodine reacts with acidified hydrogen peroxide to form iodine and water. And this reaction mixture is shaken with cyclohexane to extract the iodine. So this question is related to partition coefficient. Cyclohexane is immiscible with water. So we have our two solvents. One is cyclohexane and the other one is water, right? So they're saying that iodide ions reacts with acidified hydrogen peroxide. So iodide ions, they are reacting with hydrogen peroxide to form iodine. So we are forming iodine in this reaction and water. All right, so iodine and water is formed. This reaction mixture is shaken with cyclohexane. So this reaction mixture, iodine plus water, this is shaken with cyclohexane to extract the iodine. And cyclohexane is immiscible with water. So one of the solvent is water and the other solvent is cyclohexane. All right, Ji. So the first part of the question is identify the role of hydrogen peroxide in its reaction with iodide ions in acidic conditions, right? So the role of hydrogen peroxide in the reaction with, when hydrogen peroxide reacts with iodide ion, write an equation for the reaction as well. So first of all, in this reaction, hydrogen iodide, I think this is very obvious that it is acting as an oxidizing agent because the oxidation state of iodide is changes from -1 to 0. So H2O2 is acting as an oxidizing agent, right? And now the ionic equation. We have to write the ionic equation for this reaction. So basically hydrogen peroxide H2O2 is reacting with iodide ions, right, in acidic conditions. So that means we have H plus ions also present in the solution. And then we get, on the product side, we get iodine and water. So iodine and water, I2 plus H2O, right? And now we have to balance the reaction. So we have 2 iodine on the reactant on the product side. So we would put a 2 with iodide ions, 2 hydrogens on the product side and 2 oxygens. So that means this would be 2. And to balance hydrogen, we have to put 2 with the H plus ions. Right, so now everything is balanced except for charge. So let's just calculate the charge as well. So +2 -2, that would be 0. And on the product side, charge is also 0. So that means no need of adding the electrons, right? So this is the ionic equation. This is the ionic equation reaction happening between hydrogen peroxide and the iodide ions. All right, now next part of the question is 15 centimeter cube of cyclohexane is shaken with 20 centimeter cube of an aqueous solution containing iodide ions, right? So we have a beaker in which 20 cm cube of an aqueous solution. We have 20 cm cube of aqueous solution. So that means, let's say this is the 20 cm cube of aqueous solution. And this contains iodide ions, I2. This contains iodine. right? It contains iodine, and we have added 15 cm cube of cyclohexane into it, right? So let's suppose this is 15 cm cube of cyclohexane, C6H12. Until no further change is seen, that means equilibrium is established. So it is found that 0.390 gram of iodine is extracted into the cyclohexane. So the amount of iodine that transfers into cyclohexane is 0.390 grams. This is the amount of iodine that shifts into the cyclohexane, right? And the partition coefficient of iodine between cyclohexane and water is 93.8. So it's a very high value of partition coefficient. So that means iodine is like largely just soluble in cyclohexane, right? So calculate the mass of iodine that remains in the aqueous layer. Calculate the mass of iodine that remains in the aqueous layer. What is left into the water once we have added cyclohexane. 0.390 grams of iodine transfers into the cyclohexane, and now we have to find out that what amount of iodine is left in the aqueous solution, right? So partition coefficient, the value of partition coefficient is given. So let's just first write the formula. So partition coefficient, it is the ratio of the partition coefficient is basically the ratio of the concentration of a solute in two immiscible solvents at equilibrium. So basically here the two immiscible solvents are aqueous solution, means water, and cyclohexane. So the formula of partition coefficient would be KPC, that would be equals to grams of iodine, because it is a ratio between two concentrations, right? So no need to convert it into moles. We can just simply take it into grams, right? And this would be cancelled out. So partition coefficient, this is grams of iodine in volume of cyclohexane, C6H12, divided by grams of iodine in volume of water. So the grams of iodine in cyclohexane is 0.390. Okay, partition coefficient, value of partition coefficient is 93.8, and the grams of iodine in cyclohexane is 0.390 divided by the volume of cyclohexane is 15, right? It is 15 divided by grams of iodine in water. This is what we have to find out. So this would be X upon volume of water is 20 centimeter cube. All right, so this would be equals to 93.8. That would be equals to 0.390 divided by 15 into 20 upon X. Okay, so we have 0.390 multiply by 20, that is equals to 7.8. 93.8, that is equals to 7.8 upon 15x, right? And 93.8 multiply by 15, that would be 1407, is equals to 7.8, and the value of x would be equal to 7.8 divided by 1407. So 7.8 divided by 1407. So this is 5.5 into 10 raised to power minus 3. So 5.5 into 10 raised to power minus 3. So this is the value of partition. This is the value of grams of iodine that left in the water once most of it is extracted in cyclohexane at equilibrium, right? The amount of iodine present in water at equilibrium, this is 5.5 into 10 raised to power minus 3, right? So this is the answer for the first part of the question. And you can you can relate this value as we have a very large value. The value for the partition coefficient is very large. This is 93.8, right? And we have so that if the value of partition coefficient is very large, that means it is much more soluble in cyclohexane as compared to water. So that's why we have a very small amount of iodine in water, as compared to iodine in cyclohexane. All right, now the next part of the question is suggest how the value of partition coefficient of iodine between hexane 2-one and water compares to the value given in A2. So now they have changed one of the solvent. This time, instead of taking cyclohexane, they have taken hexane 2-one, right? Hexane 2-one. So hexane 2-one, this is a ketone. Previously we had cyclohexane, now we have ketone and water. So the question is suggest how the value of partition coefficient of iodine between hexane 2-one and water compares to the value given in A2. So the value given in A2 is 93.8. This is between iodine in cyclohexane and iodine is in water, right? So now they're asking that we have to compare the value. Like, would it be larger than the value given in A2, or would it be smaller, or would it be same, right? So the answer would be partition coefficient. The value of partition coefficient would be lower. It would be lower as compared to A2, as compared to this value 93.8. So that means iodine is less soluble in hexane 2-one as compared to with cyclohexane, right? And the reason for that is that hexane 2-one, basically iodine is non-polar. Iodine is a non-polar molecule, right? And cyclohexane C6H12, this is an alkane. This is also non-polar. And in chemistry, we know this thing that like dissolves like. So non-polar would be much more soluble in a non-polar solvent as compared to in a polar solvent, right? So cyclohexane is a non-polar solvent. Hexane 2-one, on the other hand, hexane 2-one is a polar solvent, right? It is a polar solvent. So that means the solubility of iodine will decrease, and as the solubility of iodine will decrease in hexane 2-one, the value of partition coefficient will also decrease. As numerator decreases, the value of partition coefficient will decrease. So the reason is that hexane 2-one is more polar, right? It is more polar, and therefore iodine, which is non-polar, would be less soluble in hexane 2-one. Right, so it would be less soluble, so the value of partition coefficient will decrease, will lower down. All right, the next part of the question is the group 1 iodides all form stable ionic lattice and are soluble in water. Define enthalpy change of solution. So what is enthalpy change of solution? It is the enthalpy change of solution is when 1 mole of an ionic substance, when 1 mole of substance dissolves in water, to give a solution of infinite dilution, right? So this is the enthalpy change of solution. For example, NaCl solid when dissolved in water, this gives NaCl aqueous. So 1 mole of NaCl solid dissolves in water to give an infinitely dilute solution. So the energy change which occurs, that is known as delta H solution. All right. The next part of the question is use the data in table 1.1 to calculate the enthalpy change of solution of potassium iodide. Right, now we have to calculate the enthalpy change of solution for potassium iodide, right? So the enthalpy change of solution is, and the values which we have here in the table is, first we have gaseous potassium ion and gaseous iodide ion goes into Ki solid. So that means this is lattice enthalpy. Lattice is when 1 mole of an ionic substance formed from its gaseous ions. The other energy changes. Potassium gaseous ion goes into potassium aqueous ion. So this is hydration of potassium and hydration of iodide. So we have lattice enthalpy and we have both the hydration enthalpies as well. The value which we have to find out is enthalpy change of solution. So enthalpy change of solution, let's just write all the equations and let's just draw a cycle, although we can simply solve it through the formula, but I want to draw a cycle here so that everyone can relate the energy changes, right? So enthalpy change of solution of potassium iodide, that is Ki solid. Ki solid dissolves in water, so give Ki aqueous. So this is enthalpy change of solution. This is what we have to find out, right? And if I break this Ki solid to get K plus gaseous ions and iodide ions gaseous. So this is let's just say if we convert these gaseous ions into ionic solids, so this is delta H lattice enthalpy. Right, this is delta H solution which we have to find out. This is delta H lattice enthalpy, and the last equation, that is gaseous ions converting into aqueous solution, this is delta H hydration. Delta H hydration, delta H hydration of both calcium and iodide ion. Right, so now you know how to draw the cycle as well for hydration solution and lattice enthalpy. Now we want to find out delta H solution. So that means this arrowhead would be added to this one. So let's say if we add these two and equate it with the hydrations. So the formula would be delta H lattice plus delta H solution, which we have to find out, and delta H hydrations. Right, so the lattice enthalpy is minus 629 plus solution we have to find out, and delta H hydration of potassium is minus 322 plus iodide ion minus 293. Right, so X would be equal to minus 322 minus 293 plus 629 is minus 322 minus 293 plus 629. So the answer is plus 40. All right, so this is the enthalpy change of solution for potassium iodide. Right, now the next part of the question is suggest the trend in the magnitude of lattice energies of the group 1 iodide, lithium iodide, sodium iodide, potassium iodide. Explain your answer. So we have to explain the trend in the magnitude of lattice enthalpy of group 1 iodide. So lattice enthalpy, it decreases down the group because in group lattice enthalpy depends on two factors, that is charge and radius. So charge throughout the group remains same. Every cation of group 1 has a +1 charge. Anion is same, that is iodide. So the only thing which is changing here is the cationic radius. So the cationic radius increases down the group, and as cationic radius increases down the group, the distance between the unlike charges, the cation and anion increases, and as distance increases, the attraction decrease, thus lattice enthalpy also decrease. So we can say the lattice enthalpy decreases down the group. Lattice enthalpy decreases down the group as cationic radius increases. Number of shells are increasing. So cationic radius increases down the group. The distance between ions increases, and therefore less attraction between ions, right? So the delta H lattice enthalpy gets less negative or less exothermic down the group, right? So this would be the explanation for the trend of lattice enthalpies down the group for group 1 iodides. All right, now the next part C, the concentration of copper ions in a solution can be determined by the concentration of copper ions in a solution can be determined by the reaction of copper ions with the iodide ions. So we have to find out the concentration of copper ions in a solution, right? And we are reacting copper ions with iodide ions. The iodide ions produced in reaction 1, the iodide ions produced in reaction 1 is titrated, the iodine, the iodine produced in reaction 1 is titrated against a solution containing thiosulfate ions S2O3 2- using a suitable indicator, right? So the iodine which was produced in reaction 1, that iodine is reacted with sodium thiosulfate, right? And they have given us the ionic equation, only thiosulfate ions, and this reaction is happening using some sort of a suitable indicator. So now the question is, and just remember that we have to find out the concentration of copper ions. Okay, so the 25 cm cube portion of a copper ion solution reacts with an excess of iodide ions. So the volume of copper ions solution is given, right? This solution was concentration we have to find out, its volume is given, that is 25 cm cube. So a 25 cm cube portion of a copper ion solution reacts with an excess of iodide ions. So iodide ions, they are in excess. The end point of the titration occurs when 22.30 cm cube of 0.150 mole per dm cube sodium thiosulfate or thiosulfate ions is added. Calculate the concentration of copper ions in the original solution. Okay, so for the second reaction, they have given us that the end point would occur when we added 22.30 centimeter cube of 0.150 mole per dm cube sodium or thiosulfate ions. So we have the concentration of thiosulfate ions and the volume as well. So first, now this is a question on back titrations, right? So we would solve it from the end. First, we would calculate the concentration, moles of thiosulfate ions. We have concentration and volume. So moles of thiosulfate ion S2O3 2-, that would be equal to concentration into volume. So concentration is 0.150 into volume 22.30 in centimeter cube. So we would convert it into dm cube by dividing it with 1000, right? So (22.30) divided by 1000, 0.0223 multiply by 0.150. So we have 0.00334 0.00335. This is the moles of thiosulfate ion. And now the moles of iodine, we can calculate the moles of iodine which comes from reaction 1, right? So the molar ratio between thiosulfate and iodine is 2:1. So that means whatever the moles of thiosulfate we have, the moles of iodine would be half of that, because the ratio is of 2:1. So we just simply divide the moles of thiosulfate by 2. So we get 0.0016725. So moles of iodine which we get from the first reaction, because all the iodine is coming from the reaction 1. So moles of iodine is 0.0016725. So this is moles of iodine, right? And next we would convert moles of iodine into moles of copper ions, and the ratio is 1:2. So again we have to multiply it with 2. So that means moles of copper ions Cu2 plus would be equal to 0 point, when we multiply this value by 2, this becomes 0.003345. Now we have moles of copper ions. Finally, we have to calculate the concentration. Concentration is equals to number of moles upon volume. Number of moles, we have 0.003345 divided by volume. They have already given us, that is 25 cm cube. So 25 divided by 1000. So 25 divided by 1000, that is 0.025. So 0.003345 divided by 0.025. So this is 0.1338. Right, 0.1338 or 0.134. If we round off the value, we get 0.134 moles per dm cube. This is the concentration of copper ions. So simple question on moles. Identify a suitable indicator for the titration. So I hope everyone knows the answer. So in iodine titrations, we use starch as an indicator, right? So the indicator we use would be starch. All right, so the next part of the question is that copper 1 and copper 2 both contain electrons in all 5 3D orbitals. So we have two ions of copper 1 and copper 2. So both contain electrons in all 5 3D orbitals. Sketch the shape of a 3D XY. This is a kind of question in which most of the students get confused, that how to draw a shape of a D orbital. To draw a shape of S or P orbitals, it is easy. But when they ask you to draw the shape of a d orbital, it is much confusing, right? Because d orbital, it has a kind of complicated shape. Two p orbitals are in connection with each other. So basically we have 5 d generations of d orbitals: dxy, dyz, dzx, right? So these 3 d orbitals, they lie between the planes, right? And the other 2 d orbitals, dx square minus y square and dz square, they lies on the plane. And although they lies on the different planes, but they have same energy level. So it means they are degenerated in nature, right? They have similar energy level. And now we have to draw dxy. So to draw dxy, what you have to do, just simply draw the axis. They have given us the axis, but let's just draw our own axis first, right? So just to make it clear, let's suppose this is x, this is x, right? And this is y. Okay, so this is x-axis and this is y-axis. Now dxy means all the 4 lobes would lie between x and y plane. So the first lobe would be like this, the second lobe would be like this. All right, and now the third lobe between x and y, it would be like this, and the fourth lobe would be like this. So this would be the shape of dxy orbital. All right, so now let's draw dxy on the axis they've given us. So this would be the first lobe between x and y plane, the second lobe, right? And the third lobe would be like this, and fourth lobe would be like this. All right, so this would be the shape of dxy. It lies between x and y plane. All right. Now, the next part of the question is the reaction of iodide ions with persulfate ions can be catalyzed by Fe3 plus ions. All right, so the iodide ion is reacting with persulfate ion. We have discussed it many times in classes, this reaction. Write equation to show how Fe3 plus catalyzes this reaction. So this is the most common example for the homogeneous catalysis, right? So Fe3 plus or Fe2 plus will catalyze this reaction, because in the absence of these catalysts, these two ions will react very slowly due to their negative charges. They repel each other. So Fe3 plus will act as an oxidizing agent, because itself it is going to be converting into Fe2 plus, means it is getting reduced. So it will act as an oxidizing agent. It will oxidize iodide ions into iodine. So the reaction would be Fe3 plus will react with 2 moles of iodide ions to give iodine plus Fe2 plus, and to balance the reaction we have to put 2 with the Fe3 plus and Fe2 plus, right? So this is the first part of the equation. Now because it is acting as a catalyst, so that means we have to get it back, right? So now this Fe2 plus will act as a reducing agent with persulfate ion. So the next part of the reaction would be 2Fe2 plus will react with S2O8 2 minus. This time we get sulfate ion SO4 2 minus plus 2Fe3 plus. Right, so these are the equations which shows how Fe3 plus will catalyze this reaction. So Fe3 plus, it reacts with iodide ions, and at the end we get Fe3 plus back. Okay, so the last part of this question is related to solubility product. An orange PPT of mercuric iodide, orange PPT of HgI2 forms when mercuric ions are added to Ki aqueous, iodide ions, aqueous potassium iodide. So let's say we have an aqueous solution of potassium iodide. Let's say this is some aqueous solution of potassium iodide in which K plus and iodide ions are present, and we have added mercuric ions Hg2 plus. So this Hg2 plus will react with some of the iodide ions, right? And that's why this orange PPT of HgI2 forms when mercuric ions are added to aqueous potassium iodide. The solubility of HgI2 at 25 degrees centigrade is 1 into 10 raised to power minus 7 grams per dm cube, right? So this is the solubility of mercuric iodide. That means it is partially soluble or slightly soluble salt. Calculate the solubility product of HgI2. KSP, we have to calculate the value of KSP, but first let's just write the equilibrium expression for the dissolving of HgI2. So when HgI2 is added in water, because it is partially soluble, it forms an equilibrium with the dissolved ions. So we get mercuric ions and 2 moles of iodide ions. So if we write the expression of KSP for this reaction, so KSP is the product of the ions of a partially soluble salt at equilibrium. So we have mercuric ions and iodide ions. So concentration of Hg2 plus concentration of iodide ions square, right? So the concentration, because they have given us the solubility of mercuric iodide, but this is in grams per dm cube. In KSP we need it in moles per dm cube. So let's just first convert it into moles per dm cube, and for that they have given us the MR of the mercuric iodide, which is 454.4. So the concentration in moles per dm cube of mercuric iodide would be 1 divided by 454.4. So this is 0.0022, or this would be 0.0022 into 10 power minus 7, or 2.2 into 10 raised to power minus 10. Right, minus 7 and minus 3, that would be equal to minus 10. So this is the concentration in moles per dm cube. Okay, so if we have the concentration of HgI2, if it is 2.2 into 10 power minus 10, then the concentration of Hg2 plus would also be 2.2 into 10 power minus 10, and the concentration of iodide ion would be of double of that. So it would be 4.4 into 10 power minus 10. Now the expression of KSP, we have to calculate the solubility product. So the expression of KSP is, KSP would be equal to concentration of Hg2 plus concentration of iodine, square of that. So the concentration of Hg2 plus is 2.2 into 10 power minus 10. And the concentration of iodine is 4.4 into 10 power minus 10 square. So 2.2 into 10 power minus 10 and 4.4 square, this is 19.36 into 10 power minus 20. So 2.2 19.36 multiplied by 2.2, that is 42.6 into 10 power minus 30, or this would be equal to 4.26 into 10 power 4.26 into 10 power minus 29. So the value of KSP is 4.26 into 10 power minus 29, and the unit would be moles per dm cube. Moles per dm cube is square, so that means it would be mole cube dm minus 9, right? This would be the unit of KSP, and the value of KSP is 4.26 into 10 raised to power minus 29. So this is the end of question number 1. Okay, so the question number 2 is, silicon is the second most abundant element by mass in the Earth's crust. In industry, silicon is extracted from SiO2 by reaction with carbon at over 2000 degrees centigrade. Right, so silicon is extracted by reacting it with carbon. So carbon is acting as a reducing agent in this reaction, and we get silicon. Now the first part of the question is, explain why the entropy change delta S of reaction 1 is positive. Right, so entropy is the disorder of the system. It is the measure of the disorder of the system, and disorder increases when we shift from, during a chemical reaction, when we shift from solid to liquid to gas. And they're asking that why the entropy change delta S of reaction 1 is positive. And if delta S of a reaction is positive, that means if delta S is positive, that means disorder is increasing, right? So why disorder is increasing in reaction 1? Because if we look at the reaction, on the reactant side we have 1 mole of SiO2 and 2 moles of carbon. So on the reactant side we have 3 moles of solid, right? Total 3 moles of solid, 3 moles of solid, and solid, so we have 3 moles of solid. And on the product side we have 1 mole of liquid and 2 moles of gas. So because we are shifting from solid to liquid and gas, and in liquid and gaseous phase particles are more energetic, they are more disordered, so we are shifting from an ordered to disordered phase. So why the entropy change of reaction 1 is positive? The solid reactants are converting into liquid and gaseous phase. So that's why the delta S for reaction 1 is positive. All right, next part of the question is, reaction 1 is highly endothermic. Suggest the effect of an increase in temperature, on the feasibility of this reaction. Explain your answer. Now the feasibility of reaction is determined by delta G, by the value of delta G, which is equals to, delta G is equals to delta H minus T delta S. So this is the equation through which we decide the feasibility of reaction. If delta G is negative, that means reaction is feasible, right? Delta H is enthalpy change in this reaction. Delta H, because reaction is endothermic, so that means delta H is positive. Now because we have determined in the first part that disorder is increasing, so that means delta S is positive, right? So that means T delta S is a positive term as well, and plus minus would become minus, right? So to make this reaction feasible, delta G must be negative. So if we increase the temperature, on increasing the temperature, this factor this T delta S would increase, and as T delta S would increase, the negative value, negative value would increase, and as negative value increases, overall answer would comes in negative. Right, so as temperature increases, T delta S gets more and more positive, and if this gets more and more positive, that means the overall is positive T delta S plus minus, this gets minus, so overall we get delta G as a negative value. Right, so on increasing the temperature, we have to suggest the effect of increasing the temperature on the feasibility of reaction. So we can say that the feasibility of reaction will increase, or the reaction gets more feasible. Increase as T delta S gets more positive, the delta G gets more negative, because as T delta S becomes more positive, overall answer minus of T delta S would also increase, so we get answer in negative, so the delta G gets more negative. All right, now the next part of the question is silicon is purified by first heating in a stream of HCl to form SiHCl3. The SiHCl3 formed is then distilled to remove other impurities. Right, this is the chemical reaction in which silicon is reacting with hydrochloric acid to form SiHCl3 plus hydrogen. Table 2.1 shows some standard entropy data. Use the data in table 2.1 to calculate delta S for reaction 2, change in entropy. Now, change in entropy is basically equal to, change in entropy is equals to entropy of product, sum of entropies of product minus entropy of reactant. So we just have to calculate the entropies of products and reactants, right? So the chemical reaction which we have is Si plus 3HCl gives SiHCl3 plus hydrogen. So the entropy value of silicon is 19 plus HCl is 187. So this would be 3 into 187. This gives us SiHCl3, its entropy value is 314 plus hydrogen is 131. Right, so So 3 into 187, that is 561 plus 19, that is equals to 580. This gives us 1. On the product side, the sum of entropies would be 314 plus 131. So this is 445. So delta S is equals to product minus reactant. So delta S would be equal to 445 minus 580. Sorry, delta S. So delta S would be equal to 445 minus 580. So that would be equals to minus 135. Delta S for this reaction is minus 135 joules per Kelvin per mole. Just remember this thing, that the value of delta S, entropy change, the unit of delta S is joules per Kelvin per mole. So instead of getting energy in kilojoules, we get energy in joules for delta S, right? Okay, so the next part of the question is the reaction 3 is a reversible, the reaction 3 is a reverse of reaction 2. Reaction 3 is the reverse of reaction 2. This is reaction 3 in which SiHCl3 is reacting with hydrogen. This is reverse of reaction 2 and is used to obtain pure silicon. Right? Why we are doing this reaction? To obtain pure silicon, and its delta H value is plus 219.3. So use this information and your answer to B1 to calculate the temperature in Kelvin at which reaction 3 becomes feasible. Right, so we have to calculate the temperature at which this reaction would get feasible, because delta H is positive, reaction is endothermic, that means reaction gets feasible at high temperature. So we have to calculate that temperature at which this reaction would get feasible. And if you were unable to answer B1, you should use delta S is equals to minus 150 joules per Kelvin per mole. But we already have calculated delta S, so we would use that value, right? So to calculate the temperature, or to determine the temperature at which this reaction would get feasible, we would use this statement that delta G is equals to 0. This is the equation, this is the condition for the equilibrium, right? So this is the condition. We just want to calculate the temperature for this condition, and above this temperature the reaction would be feasible. So delta H minus T delta S, that means delta G is equals to delta H minus T delta S, so that would be equals to 0. Now delta H is 219.3 minus temperature we have to find out, and delta S. Now we have calculated the delta S for the previous reaction, and that was minus 135. But reaction 3, now we need delta S for reaction 3, and reaction 3 is reverse of reaction 2. So that means whatever the delta S value for reaction 2 was, we have to switch the sign, right? We have to change. If it is negative, if the delta S was negative for reaction 2, it becomes positive for reaction 3. If it was positive for reaction 2, it becomes negative for reaction 3. So the delta S for reaction 2 was minus 135 minus 135. So that would becomes plus 135. Okay, that would be 135, and because delta S is joules per Kelvin, but now we have to convert it into kilojoules. So to convert it into kilojoules, we have to divide it by 1000. Now we have to calculate the temperature. This whole value is equals to 0. So 135 divided by 1000, that is 0.135. So minus T is equals to, or 219.3, that would be equals to 0.135 T, or temperature would be equals to 219.3 divided 0.135. So the temperature at which this reaction would get feasible is 219.3 divided by 0.135. So this is 1624.4 Kelvin. So this is the temperature at which this reaction would get feasible, right? Now, the last part of the question is, silicon can also be produced by the electrolysis of SiO2 dissolved in molten calcium chloride. The relevant half equation for the cathode is shown: silicon dioxide reacting, gaining electron to convert into silicon. Means they're saying that silicon can also be produced by the electrolysis of SiO2, and you can see in this reaction that SiO2 gains electron at cathode and converts into silicon. Now, the question is, calculate the time in seconds required to produce 1 gram of silicon by this electrolysis using a current of 6 amperes. Right, so we have to calculate the time required to produce 1 gram of silicon by the electrolysis using a current of 6 ampere. Assume no other substance are produced at the cathode. Alright, so first what we have to do, we would convert this grams of silicon, which we need, into moles, right? So moles of silicon would be equals to given mass upon MR. So mass of silicon is 1 divided by 28. 28 is the molar mass of silicon. So 1 divided by 28, that is 0.0357. 0.0357. Now let's just find out the moles of electrons needed to produce this much moles of silicon. So the molar ratio of silicon electron is 4:1, right? So 4 moles of electron gives 1 mole of silicon. So that means ratio is of 4 to 1. So if we have 0.0357 moles of silicon, so what moles of electrons would be needed? So that would be 0.0357 multiplied by 4. So this would be 0.1428. So moles of electron is 0.1428. Right, so next we have to calculate the charge carried by this much moles of electron. Now we know that 1 mole of electron carries 96,500 coulomb, 1 Faraday, right? So if we have 0.1428, so what amount of charge would be carried by this much moles of electron? So that would be equals to multiply by 96,500. So that is 13785.71. This is the charge carried by. So the charge carried by electrons is 13785.7. And finally, we need to calculate the time in seconds required to produce 1 gram of silicon. So Q is equals to A into T, or time is equals to Q upon A. Right, so charge was 13785.7 divided by amperes. What we pass 6 amperes current, so this is 6, right? So this would be divided by 6, and the final answer is 2297.6 seconds. Right, so this is the final answer, and this is the time required to produce 1 gram of silicon by the electrolysis using a current of 6 ampere. Alright, so this was simple question, and this is the end of question number 2. Alright, so the next question is from transition elements. Titanium is a transition element in period 4. It is commonly found as TiO2 in minerals. Define transition element. So what is a transition element? An element that can form one or more stable ions with partially filled D stable ions with incomplete or partially filled D subshell. Right, so this is the definition of transition elements. Alright, now the next part of the question is identify 2 typical properties of transition elements. So transition elements have various typical properties. First of all, they give variable oxidation states, right? They show variable oxidation states in their compounds, show variable oxidation states. For example, iron could be either +2 or +3, vanadium shows different oxidation states. And secondly, they can act as catalyst, right? They form complex ions, they give colored solutions. So these are all typical properties of transition elements. So you have to just write any 2 of them. Now the next part of the question is the TiO2 plus ion forms when TiO2 reacts with an excess of dilute sulfuric acid. So when titanium oxide reacts with sulfuric acid, we get TiO2 plus. TiO2 plus can be reduced by zinc metal in acidic conditions to form a purple solution containing Ti3 plus. TiO2 plus is a colorless ion. Suggest why. Right. So now they're asking us that why TiO2 plus, normally transition elements or their ions, they give colored solutions, but TiO2 plus is colorless, and we have to give a reason for this. Now the color theory is that when a transition element forms a complex, its degeneration breaks, and the d orbitals, they have energy difference which lies in visible region. So when light falls, some of the energy would be absorbed by the lower energy level electron for the jump, and the rest of the energy would be transmitted, and that transmitted light gives the color to the solution. But here in TiO2 plus, they're saying that it is a colorless ion, right? It is a colorless ion. Okay, so to explain it, that why TiO2 plus does not show, does not give a color, or it is a colorless ion. First, just find out the oxidation state of titanium in TiO2, TiO plus. So in TiO, sorry, 2 plus, right? So oxygen is -2. So to give it an overall charge of +2, that means titanium would have a charge of +4. And let's look at the atomic number of titanium. So the atomic number of titanium is 22, right? This is 22. So if we write the electron configuration of titanium, titanium has an atomic number of 22, that means 22 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d2. So to form Ti4 plus, that means 2 electrons from 4s would be lost and 2 electrons from 3d would be lost. So there are no electrons present in 3d orbitals when it forms Ti plus 4 ion, right? So when it forms Ti, so the color only comes when there is electrons present in d orbitals and these electrons jump into a higher energy level. But if there are no electrons present, right, there are no d electrons in TiO2 plus, right? So it cannot absorb energy in the visible region, cannot absorb energy in visible region or light in visible region, right, as it does not has any electrons present in d orbitals. That energy gap between d orbitals, that is responsible for the color of the complex. But if there are no electrons present in d subshell or d orbitals, that means it would be a colorless solution. So no wavelength absorbs in visible range of electromagnetic radiations, right? So that's why TiO2 plus does not give a color solution. So this is a type of a new question. We haven't have any questions like these in past papers. So this is a new question for you guys, right? So this is why TiO2 plus does not show color, because it has no electrons. So just remember this thing, that to give a color, the transition element must have electrons present in d orbitals. If it has no electrons present in d orbital, that means it cannot absorb radiations in visible region, and that means it would be a colorless solution, right? Give the electronic configuration of an isolated Ti3 plus ion, right? So Ti3 plus ion, that means 1s2, 2s2, 2p6, 3s2, 3p6, 18. Then 4s electrons would be lost. There would be no electrons present in 4s and only 1 electron present in 3d. So this would be the electron configuration of Ti3 plus. Write an ionic equation for the reduction of TiO2 plus by zinc metal in acidic conditions. So reduction of TiO2 plus, TiO2 plus reacting with zinc in acidic medium, that means H plus. So TiO2 plus in TiO2 plus, titanium has an oxidation state of +4 and it changes from Ti +4, it gets reduced into Ti3 plus zinc will be oxidized into Zn2 plus. Alright, now we have to balance this equation, plus we get water H2O. Alright, so we would have zinc is losing 2 electrons, titanium is gaining only 1 electron, plus 4 to plus 3. So that means to balance electron we have to multiply TiO2 with 2, and on Ti this side as well. So we would place 2 with TiO2 plus and Ti3 plus. So that means now we have, now the charge is balanced, number of electron loss and gain are balanced, and now we have 2 oxygens on the reactant side. So that means 2H2O, and to balance hydrogen it would be 4H plus. So this is the ionic equation for the reaction of TiO2 plus with zinc metal. Alright. Now the next part of the question is, acidified Ti3 plus reacts with oxygen dissolved in water as shown. Ti3 plus reacts with oxygen dissolves in water as shown, and delta G for this reaction is given. Right, delta G for the reaction is given. Delta G is Gibbs free energy. The standard reduction potential of O2 of oxygen is half. The standard reduction potential of the reduction of oxygen is plus 1.23 volt. Calculate the standard reduction potential in volt of the TiO2 plus, Ti3 plus, this half cell. We have to calculate the reduction potential of this half cell, this one, right? Show your working. So we know this thing that to find out the reduction potential of any half cell, we have 2 half cells here. One is TiO2 plus Ti3 plus, and the other half cell is O2 H2O, right? Its E cell, its reduction potential is given, which is 1.23, right? And they're asking for the reduction potential of this half cell. So basically in this reaction, if we look at the oxidation numbers, we can find out that titanium is being oxidized in this reaction. From plus 3 it goes into plus 4, so that means it is being oxidized, and that means that suggests that oxygen is working as an oxidizing agent, right? So E cell would be equal to E reduction minus E oxidation, and E oxidation is the reduction potential of this half cell. But to find out this oxidation potential or this reduction potential of TiO2 plus Ti3 plus, they have already given us the reduction potential of oxygen half cell, right? This is what we have, but we do not have E cell. So if we get E cell, then we can easily find out this reduction potential of TiO2 plus and Ti3 plus. So to find out E cell, we would use the relation between the Gibbs free energy and the cell potential, which is a new topic to the syllabus, and you will have learned this reaction that delta G is equals to negative of NFE naught cell. So this is the relation between delta G and E naught cell, right? And remember this thing that in this particular reaction, delta G is being taken in joules per mole, right? So this is, they have given us delta G in kilojoules per mole, but we have to convert it into joules per mole. Alright, so the value of delta G is 436.1 multiplied by 1000. So that is equals to 436,100 minus 436,100. This is the value of delta G in joules per mole. N is the number of electrons involved. So how many electrons are involved here? 4 electrons are involved. So that means the value of N is 4 into F is Faraday's constant. Its value is fixed, 96,500, and E naught cell, this is what we have to find out. So 4 into 96,500. 386,000. So 436,100 minus 386,000x. Negative signs would be cancelled out, and x would be equal to 436,100 divided by 386,000. So that is 1.13. So this is the cell potential, 1.13 volt. 13 volt. This is the cell potential. So now we have the cell potential. Now we can simply calculate the standard reduction potential of titanium half cell. So E cell is 1.13. Reduction potential of oxygen half cell is 1.23 minus X. So 1.13 minus 1.23 is equals to minus X. So 1.13 minus 1.23. So that is equals to 0.1. Negative signs would be cancelled out, and this would be equal to 0.1. So this is the reduction potential of titanium half cell. So first we calculated, they have given us the value of delta G. So that's why first we calculated cell potential from the relationship between delta G and cell potential, and afterwards we put it in the formula of E cell and calculated the reduction potential of titanium half cell. Okay, now the next part of the question is, when aqueous citrate ions are added to Ti3+, this complex forms. Explain in terms of d orbitals why Ti3+ is able to form complex ions. Why it is able to form complex ions? Because it has vacant d orbitals. Any transition element, it can form complex ions due to the availability of vacant d orbitals, which can act as an acceptor in dative bond formations. So as it has vacant d orbitals which can act as acceptors in dative bond formation. With ligands. Acidified titanium complex does not react with oxygen dissolved in water, unlike acidified Ti3+. Suggest what this means for the value of the standard reduction potential of the following half cell. They're saying that Ti3+ can react with oxygen dissolved in water, the same reaction for which we calculated the E cell. So that means in this reaction oxygen was acting as an oxidizing agent, and it was oxidizing titanium plus 3 ions. But this reaction cannot occur with this complex. If we react TiC6 H5O7 3 minus with oxygen in water, they're saying that no reaction will occur. Does not react with oxygen dissolved in water. Right, so suggest what is meant for the value of the standard reduction potential of the following half cell. So from this information, based on this information, what can be deduced about the value of reduction potential for this half cell? The value of the reduction potential of oxygen half cell was 1.23, and oxygen was acting as an oxidizing agent, means itself it is being reduced. So for a half cell to be reduced, it must have a higher or a more positive E0 value. And if this complex is not being oxidized by oxygen half cell, so that means it has a higher or it has a more positive reduction potential value than the oxygen half cell. So we can say that the E0 will be more positive than plus 1.23 of oxygen, right? Which makes the delta E negative, and that's why reaction would not occur, because for the reaction to happen, E0 cell must be positive. So if it is higher, so that means reaction cannot happen. So if the half cell in which oxidation has to be taken place, if it has more positive E naught value, reduction potential value, that means no reaction will occur. So the E naught value would be more positive than plus 1.23. That means oxygen cannot oxidize, cannot act as oxidizing agent for this particular complex. Alright, now the next part of the question is some reactions of TiO2 plus are shown in figure 3.1. The anion ACAC minus is a bidentate ligand, and these are some reactions. Figure 3.1, the titanium ion in TiF6 2 minus and TiACACCl2 have a coordination number of 6. What is meant by coordination number? So what is meant by coordination number? It is the number of bonds being formed by the number of dative bonds formed by the central metal ion. How many dative bonds it is being forming. Write an equation for the formation of TiF6 2 minus from TiO2. So TiO2, this reaction, TiO2, titanium oxide reacts with chlorine to give, this reaction. They are talking about this reaction. So TiO2 reacts with HF to give TiF6 2 minus. So that means we have 6 moles of HF, right, and 3 moles of and 2 moles of water, because 2 oxygen, so that means 2 moles of water, and to balance remaining hydrogens, because on reactant side we have 6 hydrogens, product side 4 hydrogens, we would add 2H plus. Now let's just find out the charge, overall charge. On the reactant side charge is 0 because there are no charge particles on the reactant side, no charge, so that means charge is 0. On the product side this is minus 2 and this is plus 2, so minus 2 plus 2 would be also equal to 0, right? State what is meant by bidentate ligand. So what is a bidentate ligand? Which can donate or which can make 2 dative bonds with the central metal ion. Species which can form 2 dative bonds due to the availability of 2 lone pairs. Right, so any ligand which can form 2 dative bonds with the transition metal ion, that means it is a bidentate ligand. Alright, now the next part of this question is this complex shows both optical and geometrical cis-trans isomerism. This exists as 3 stereoisomers, right? It has 2 bidentate ligands, TiACAC2Cl2. These are 2 bidentate ligands and 2 monodentate ligands. So if the transition metal ion has 2 bidentate and 2 monodentate ligands, that means it can exhibit both optical and geometrical isomerism, right? The structure of one stereoisomer of TiACAC2Cl2 is shown in figure 3.2. And because the bond angle between 2 chlorine is of 90 degree, that means it is a cis-trans isomer, right? It is a geometrical isomer. Complete the structure of the other 2 stereoisomers of this complex, right? So now we have to draw the 2 geometrical isomers. When both the monodentate ligands are 90° apart, that means it is cis. And if they are 180° apart, let's suppose we draw the other two isomers. So this is one Cl and this is another Cl, and this is ACAC and ACAC. So this is another isomer, and this would be trans because in this isomer both the chlorine atoms are 90° apart. So this is trans. And now we have to draw the optical isomer with respect to this structure. So an optical isomer means two non-superimposable mirror images, right? So two non-superimposable mirror images would be, we would shift the dotted line here and the wedge would be shifted here. So now we have Cl on this side and Cl on this side. So now we are drawing the mirror images, right? And this is and ACAC. So this one and this one, they two are the mirror images of each other, right? They are non-superimposable mirror images. So that means if I name the structure, let's suppose if this is A and this is B and this is C. So A and C are optical isomers and A and B are geometrical isomers. Alright, and the last part of this question is the ACAC anion is symmetrical. Deduce which, if any, of stereoisomers 1, 2 and 3 are polar. Explain your answer. Which of these isomers are polar? So those isomers, a trans isomer would be non-polar. Trans isomer would be non-polar because the polarities would be cancelled out. This polarity would be cancelled out by this one, and this polarity would be cancelled out by this one because same ligands are on the opposite side. But the two optical isomers, they would be polar in nature because the dipoles are not cancelled out. So we can say that, so isomer 1 and its optical isomer are polar in nature. Okay, they too are polar in nature. So dipoles do not get cancelled out. Alright, so this is the end of question number 3. Alright G, so the next question is related to organic chemistry. Compound F and J are shown in figure 4.1. So we have two different compounds, F and J. F and J both contain the arene functional group, this benzene ring. Benzene rings are known as arenes. So they both contain this arene functional group. Identify the other functional groups in F and J. What are the other functional groups present in F and J? So in F we have this phenylamine, or so we have amine and carboxylic acid. Right, so F contains phenylamine and carboxylic acid, and J has this ester group and phenol. So ester and phenol. So these are the functional groups which are present in F and J other than arene. Alright, next part of the question is, state the number of chiral centers. The number of chiral centers in a molecule of F and in a molecule of J. So we have to count the number of chiral centers in F and J. So first let's just erase all this. Right, so in F, you can see that there are no chiral centers because this carbon has a pi bond and all these carbons are sp2 hybridized. So that means no chiral centers in F. So in F there are 0 chiral centers, and in J we have this 1 chiral center, then It is the second chiral center. This one is not a chiral center because it is attached to both CH3, right? So there are two chiral centers present in J. So 0 and 2. All right. A student proposes a multi-step synthesis of F from benzene as shown in table 4.1. So in table 4.1, they have given us the synthesis of F from benzene, right? This is benzene. Complete table 4.1 by providing relevant details of the reagents and conditions for step 1 and 4 and the structure of product D. So we have to write the reagent and condition for step 1. In step 1, what is happening? We have this benzene ring converts into methyl benzene. So this is substitution reaction, right? This is alkylation of benzene and methyl group is being attached. So that means the reagent is CH3Cl in the presence of AlCl3 as a catalyst, right? And then the structure of D. So the structure of D, right? So this is methyl benzene, and methyl benzene is reacting with concentrated nitric acid and concentrated sulfuric acid. So that means this is nitration, right? We are adding NO2 group to the benzene ring, substituting NO2 group to the benzene ring. And because this methyl group is a 2,4 director, so it will direct the incoming nitro group to 2 and 4. But if you look at the structure, you can see that NO2 group is on the 4th carbon if we count it from here. So this is 1, 2, 3, 4. So that means this is 4 nitromethyl benzene. So the structure of D would be methyl, and we have an N2O on the 4th carbon atom, right? And how would we know that this is 4th carbon atom? Because the methyl benzene, if you look at reaction number 3, so in reaction 3, D is the same structure which is formed in reaction 2, is reacting with hot alkaline KMnO4 with then dilute sulfuric acid. So that means it is oxidation. And we know this thing that alkyl benzenes, they can be oxidized and they convert into benzoic acid. So this is the CH3 group. This is the CH3 group oxidized, right? So that's why I've attached N2 on the 4th carbon, because before oxidation, this was CH3. This was CH3 before oxidation, and it directs the N2O on the 4th position. So I think reaction 2 and 3 would be pretty much clear to everyone. And now we have to write the reagents for reaction 4. So reaction 4, in reaction 4, what is happening, that COOH group is on its place. N2O is being changed into amine. So that means it is reduction, right? And for reduction, we use, for the reduction of nitrobenzene, the reagent is tin and concentrated hydrochloric acid, right? And we have to heat this reacting mixture. So we get this amine group, right? So these are all the reagents and conditions and structures that we have to draw. Next, they're saying in a second multi-step synthesis, the student changes the order in which the reagents and conditions are used, right? The reaction scheme is shown in figure 4.2. And this time what he's doing, if you look at this reactions, that he converted benzene into methyl benzene. Then before nitration, what he does, like in the previous reaction, he first converted methyl into benzene into methyl benzene. Then he did the nitration of methyl benzene. But this time, and afterwards he did the oxidation, but this time he's, once he converts benzene into methyl benzene, he further do the oxidation reaction. And after oxidation, he's doing nitration, right? So this time, the order is that first substitution reaction in which you get methyl benzene, then oxidation, we get benzoic acid, and finally nitration. So due to which the structure would have a slight change in it, and that's why instead of getting compound F, now we are getting compound G. So they're saying draw the structure of G and explain why G is the major product of the synthesis rather than of E. So basically COOH group, as methyl was 2,4 director and alkyl was 2,4 director, COOH is 3 director, right? So it directs the incoming group to the 3rd position. So that means this time the structure of G would be, this is benzene ring and COOH and 1, 2, 3. So this would be NO2. right? So basically, now we have to explain why this all is happening, because COOH group is 3 director. It directs the incoming group on third position of the ring. ठीक है जी, of ring. Plus it is a deactivator as well. It imparts the positive charge on the ring, so that due to which the ring gets less reactive, right? But for now we were just describing the directing effect of the carboxylic acid. All right. Now, in the next part of the question, it is saying that J reacts under suitable conditions with NaOH aqueous alkalinic medium, and after acidification of the reaction mixture, compound K and L are formed. So basically, first we are reacting J with NaOH aqueous, and afterwards acidification occurs, due to which K and L forms. So there are two reactions involved here. First reaction is reaction of J with aqueous NaOH, and then acidification with HCl. So they're asking that give the molecular formula of L. So when we react this compound, this J with NaOH aqueous, so I hope everyone knew this thing, that hydrolysis would occur as we have this ester group present. So this ester group would be hydrolyzed in the presence of aqueous NaOH. It would break, and it breaks into salt and alcohol, right? So this oxygen would gain a hydrogen. So the molecular formula of L, would be, count the number of carbon atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9. C9. Hydrogen 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is C9, because this oxygen would give a hydrogen as well. So C9H18, and this one oxygen. So this is oxygen. And let me just draw the structure of L as well. So this is the structure of L. All right, so this is the structure of L, and the molecular formula is C9H18O. Next, it is saying that state the two types of reactions that occur when J reacts with NaOH aqueous. When J reacts with NaOH aqueous, so two types of reaction. First, hydrolysis occurs, basic hydrolysis, or you can simply write hydrolysis occurs. And due to hydrolysis, we would get salt, not this carboxylic acid. Instead of this hydrogen, we get Na, but then we add acid, and acid would release H plus ions, and it would attach with oxygen. So this is acid-base reaction. We get the carboxylic acid back. So the second reaction would be acid-base reaction. All right. Now the D part is K can also be synthesized from phenol, right? We are synthesizing K. This is K, and they're saying K can also be synthesized from phenol, and they have given us some reactions of phenol, right? Reaction 1, reaction 2, reaction 3. Now let's move on with the question. So they're saying write an equation for the formation of M in reaction 1. So M in reaction 1. So in reaction 1, what we are doing is we are reacting phenol with sodium, and as phenol is slightly acidic, so sodium will displace the hydrogen. So the formation, write an equation. So the equation would be C6H5OH. This is phenol reacting with sodium. So the H would be displaced by sodium. So we get C6H5O and A plus hydrogen gas, right? And to balance this, we write 1/2 with hydrogen. So basically this is acid-base reaction. Acid plus metal gives salt and hydrogen gas, and this is salt. Draw N the product of reaction 2. reaction 2. In reaction 2, we are reacting phenol with excess bromine. So when we react phenol with excess bromine, phenol is an activator, right? Phenol is an activator, so it activates the ring, due to which all three positions would be occupied. And when phenol reacts with bromine, the product of the reaction would be, now this was phenol, and it makes all the 2, 4, and 6 positions active. So basically on position number 4 we get a bromine, position number 2, 4, and position number 6. So this would be the structure of 2,4,6 tribromophenol. Now the next part of question is explain why phenol is a weaker acid than K. Why phenol is a weaker acid than K. So what is K? K is carboxylic acid. If you look at this structure, so K is carboxylic acid. So that means they are asking that why phenol is weaker acid as compared to carboxylic acids. So in case of phenol, let's suppose if this is phenol, when it loses proton, it becomes O negative. Now phenol is a stronger acid as compared to alcohol, and the reason is that this lone pair or negative charge of oxygen, it gets delocalized with the ring. It gets delocalized with the ring, and it is now less available for the protonation. But when we compare it with organic acids, carboxylic acids, right? So if I compare it with carboxylic acid, so what happens is this is carboxylic acid K, right? So what happens is that when this carboxylic acid will ionize, so we get C double bond O, O negative, and OH. Now this oxygen as compared to the oxygen of phenol, this is now less available for the even more, this is even less stable. So this is even less available for protonation as compared to the phenoxidine. This is basically, this is phenoxidine, right? So the carboxylate, this is carboxylate. So we say that carboxylate is more stable. Carboxylate is more stable, and phenoxidine is less stable, because in carboxylate the resonance occurs between these two oxygens. So the pi electrons or the negative charge is delocalized between these two oxygens, equally delocalized. And in case of phenol, although the lone pair of oxygen is delocalized with the ring, but still oxygen is the most electronegative part of the structure. So that means most of the negative charge is on the oxygen. And compared to that, carboxylate, it has electron distribution. It has even electron distribution between both the oxygen atoms. So that's why it has a lesser chance of accepting a proton, and that is why it is more acidic as compared to phenol. So carboxylate is more stable as negative charge is delocalized between both oxygens, due to which it is less available for protonation or backward reaction. So that's why it is more acidic, because its negative ion is more stable. The strength of a weak acid, it depends on how stable negative ion it forms, how stable conjugate base it forms, right? Or you can say that what are the chances of backward reaction. So more chances of backward reaction means less stronger acid, right? Okay, and the last part of this question is that phenol and benzene both reacts with nitric acid as shown in figure 4.5. Now phenol reacts with dilute nitric acid for the nitration, but benzene reacts with concentrated nitric acid in the presence of a catalyst. So both, basically phenol is a derivative of benzene, but benzene require more harsh conditions as compared to phenol. Phenol is reacting in the presence of dilute nitric acid, nitration is happening, but in case of benzene we need concentrated nitric acid. So the reason for this is that we can say that the p orbital of the phenol, like this is the phenol. Now in phenol, oxygen has two lone pairs, and one of these lone pairs it gets on the same plane with the p orbitals of ring, and it gets delocalized over the ring. So negative charge intensity rises on the ring, right? And due to which it becomes more reactive. So we can say that p orbitals on oxygen, the lone pair of oxygen or the electron present in p orbitals overlaps with ring pi electrons to get more stable, right? Or we can say the lone pair of oxygen is delocalized over the ring. Lone pair of oxygen is delocalized over ring, right? So electron density increases on ring. Electron density increases on ring and it becomes more reactive. Gets more electron density increases, so it attracts electrophiles more, because the major reaction of benzene is electrophilic substitution. So ring, it attracts electrophile more, and hence reactivity increases. So this is why phenol is more reactive, and phenol reacts with dilute nitric acid, but benzene has to react with concentrated nitric acid, because phenol is much more reactive as compared to benzene. Phenol makes the ring activating. Alright, so this is the end of question number 4. Alright, so the second last question is 2-chloropropanoic acid. This is 2-chloropropanoic acid structure is used in many chemical synthesis. An equilibrium is set up when 2-chloropropanoic acid is added to water. Write an equation for this reaction. So when 2-chloropropanoic acid is added to water, it releases H plus ion to water. So the chemical reaction would be CH3 CH Cl COOH, 2-chloropropanoic acid. When added to water, it releases proton to water. So water becomes hydroxonium or hydronium, plus we get CH3 CH Cl CO2 minus. Right. So this is the chemical reaction when 2-chloropropanoic acid is added to water. Then in the next part, it is saying that 0.150 moles of 2-chloropropanoic acid dissolve in 250 centimeter cube of distilled water. To produce a solution of pH 1.51, calculate the pKa of 2-chloropropanoic acid. Now, to calculate the pKa value, first we have to find out the H ion concentration, for which we have pH value already given in the question. So first of all, let's determine the H ion concentration in this weak acid solution, and that would be determined from the pH formula. So pH is equals to negative log concentration of H plus ion, and the concentration of H plus ion would be equal to shift anti-log minus 1.51, right? So this would be equal to 10 to the power minus 1.51, and this is 0.0309. So this is the H ion concentration, 0.0309. Then we have to find out the Ka value. In the question, they've asked us to calculate the pKa value, but first let's find out the Ka value. So Ka is equals to concentration of H plus ion, concentration of CH3, CH, Cl, CO2 negative over the concentration of unionized acid, which is CH3, CH, Cl, COOH. So the concentration of H plus ion is, we have just calculated it, that is 0.0309. And in a weak acid solution, whatever the concentration of H plus ion, the concentration of negative ion would be same. Concentration of H plus ion and the concentration of negative ion would be same in a mono basic acidic solution. So that means we have 0.0309, and the concentration of negative ion would also be 0.0309 divided by the concentration of weak acid. They have given us the moles and the volume. So let's just convert it into concentration. So C is equals to N upon V. C is equals to N upon V. So moles 1.150 divided by volume is 250 divided by 1000. So that is 250 divided by 1000, that is 0.25. So 0.150 divided by 0.25. So this is the concentration of unionized acid, which would remain same until the equilibrium because it is partially ionizing. So the concentration of weak acid would be 0.6, right? And now if we solve this, all these values, so we get the answer for Ka, right? So Ka would be 0.0309 square. So that is divided by 0.6. So this is 0.00159. This is the value of Ka. So the value of Ka is 0.0015 or 16. Right, and now finally we have to determine the pKa value. So pKa is equals to negative log Ka. So log of Ka, log of 0.0015. This is minus 2.82. Minus would be would convert into plus. So the answer would be 2.82. So this is the final answer. This is the value of pKa for 2-chloropropanoic acid, right? So this is the simple calculation. First we determined the H ion concentration, then Ka value, and finally pKa value. Okay, so the next question is an equal concentration of aqueous propanoic acid has a pH value of 2.55. Aqueous propanoic acid, right? So chloropropanoic acid has a pH value of 1.51 and propanoic acid has a pH value of 2.55. Explain the difference in the pH of solutions of equal concentration of 2-chloropropanoic acid and propanoic acid. So we know this thing that 2-chloropropanoic acid, this is 2-chloropropanoic acid, this is more acidic than propanoic acid. And the reason is this chlorine group, as it is electron withdrawing, it attracts the electron density towards itself, due to which once chloropropanoic acid loses proton, once it loses proton, CH3, CH, Cl, C double bond O negative plus H plus. So the Cl being more electronegative, it attracts the electron density towards itself, due to which the negative charge intensity on carboxylate ion decreases and it becomes difficult for it to gain proton. And in case of propanoic acid, there is no chlorine attached, so that's why it can attract the electron easily, propanoic acid. So that's why chloropropanoic acid has a lower value of pH. That means it is a stronger acid as compared to propanoic acid. So in chloropropanoic acid is more acidic due to electron withdrawing nature of Cl, right, which makes the or you can simply say which lowers the negative charge intensity, which lowers the negative charge intensity on oxygen or carboxylate ion, due to which it becomes difficult to regain proton. So it gets stabilized. It gets stable. Right, as compared to propanoic acid. In propanoic acid, there is no chlorine. It is attached to R groups, which are electron releasing. So that's why propanoic acid is less acidic as compared, propanoic acid is less acidic as compared to chloropropanoic acid. Now, the next part of the question is when chloropropanoic acid reacts with aqueous ammonia, alanine forms. This is the structure of alanine. Alanine is an amino acid. Its isoelectric point is 6.1, right? State what is meant by isoelectric point. So isoelectric point is the pH at which a molecule has no overall dipole, right? It is neutral or it exists in zwitterine formation, right? So this is known as isoelectric point. All right, next part of the question is give the structural formula of alanine at pH 2. So at pH 2, that means at pH 2 there would be pH 2 is an acidic range, so that means we would have large number of H plus ions, right? So COOH will exist in this form. It would be unionized, it gains proton, and NH2 due to its lone pair will also gain proton. So this becomes NH3 plus CH3 CH NH3 plus it gains proton COOH. So this is the structure of alanine at pH 2. All the amino acids at lower pH, they exist in positive ion formation, and at higher pH exist in negative ion formation. Alanine exists as a pair of optical isomers. The structure of one optical isomer is shown in figure 5.2. Draw the three-dimensional structure of the other optical isomer of alanine. So the other optical isomer of alanine would be CH3. This NH2 would move to this side, NH2. Dotted line would be on this side, H. And we get COOH. Right, so this is the mirror image of 2-chloropropanoic acid. Alanine. And then in the next part of the question is saying that polymer C forms when the reaction between alanine and 4-amino-butanoic acid. Polymer C forms from the reaction between alanine and 4-amino-butanoic acid. Draw a repeat unit of C. The functional group formed should be displayed. Right, so we have alanine NH3 CH3 NH2 CH3H C double bond OH. This is the structure of alanine reacting with 4-amino-butanoic acid. 1, 2, 3, 4. This is butanoic acid, 4-amino. So we have on fourth carbon we have NH2 group, right? So condensation reaction would occur. This carboxylic acid would lose OH, and it would lose one of its hydrogen, so it becomes H2O, and we get, or we say this would lose its hydrogen and this would lose OH, right? So we are left with NH, C, CH3H, C double bond O, N, H, 1, 2, 3, 4. Right, so this is the structure of the polymer C, which forms from the reaction between alanine and 4-amino butanoic acid. This is the condensation polymer, right? So we have drawn a repeat unit from when one alanine and 4-amino butanoic acid reacts with each other. So state the type of polymerization shown in B4. So this is condensation polymer because mild link is being formed, right? And water molecule is released. So this is condensation polymer. Scientists are investigating C as a replacement for polypropene, right? This polymer, the structure which we have drawn here. So scientists are investigating C as a replacement of polypropene in packaging. So suggest an advantage of using C instead of polypropene. So polypropene is an addition polymer which is non-biodegradable. Polymer C would be biodegradable. So we can say that C is biodegradable. Right, C is biodegradable. It can be easily hydrolyzed. By hydrolysis, it decomposes, right? All right, so the next part of the question is, a student studies the reaction of chloropropanoic acid with aqueous ammonia to determine the reaction mechanism. The student finds that when chloropropanoic acid and ammonia are added in a 1-to-1 stoichiometric ratio, the conjugate acid and base of the reactants are quickly formed. Means when they react with each other, when chloropropanoic acid and ammonia react with each other in a 1-to-1 ratio, the conjugate pairs immediately form. Identify the conjugate acid-base pair in reaction 1. All right, so let's suppose in this reaction, chloropropanoic acid, it releases proton, and once it loses proton, it becomes this propanoate ion, right? So once an acid loses proton, we can say that chloropropanoic acid is an acid. This is conjugate acid base pair 1, CH3 CH Cl COOH. This is the acid, and its conjugate pair is, once it loses proton, it becomes CH3 CH Cl CO2 minus. This is its conjugate pair. And the other conjugate acid base pair is ammonia is acting as a base because it is accepting proton, and its conjugate acid would be NH4 plus. Once it gains proton, it becomes NH4 plus. So this is conjugate acid, right? So we can say that this is an acid and this is conjugate base, whereas ammonia is a base and ammonium ion is a conjugate acid. All right. Then in the next part of the question, in an excess of ammonia, propanoate ion, chloropropanoate ion undergoes a nucleophilic substitution reaction. This chloropropanoate ion reacts with ammonia in a nucleophilic substitution reaction, and NH3 acts as a nucleophile and it replaces Cl. You can see that amine group is placed in the position of Cl, and Cl minus leaves the compound or the ion as a leaving group. A student investigates the rate of reaction of reaction 2, right? He's studying the rate of reaction 2. The student mixes chloropropanoic acid with a large excess of ammonia. Chloropropanoic acid with a large excess of ammonia. The graph in figure 5.3 shows the results obtained. So this is the graph of concentration of chloropropanoic acid against time. The concentration of ammonia is in large excess, right? And he's observing the change in concentration of chloropropanoic acid with respect to time. Okay, so the next part is use the graph in figure 5.3 to show that reaction 2 is first order with respect to chloropropanoic acid. So just to prove that it is first order, we have to look for the half-life, first half-life and second half-life, and if both the half-lives are same or almost same, that means it is first order reaction. So it starts with 0.0021, right? So the half of 0.021 would be 0.021 divided by 2, that is 0.0105. So 0.0105, this would be this value, right? And now we have to look at the x-axis where this line cuts the x-axis. So this would be at, this cuts at 440, 460, around 500, right? So this is around 500. So the first half-life is around 500, and now the second half-life 0.1005, 0.0105 divided by 2, so that would be 0.005. So 0.005 right, so this is 1020. So around the first half-life was of 500 seconds, and the second half-life is around of 510 seconds, right, or 20 seconds. So this is almost same, right? So we can say that the first half-life and the second half-life, they both are same. So that means this is first order reaction with respect to chloropropanoic acid. So use the graph in figure 5.3 to show that the reaction 2 is first order with respect to chloropropanoiodine. So we can say that the so you have to show at least 2 half-lives. So the half-life for the reaction is constant. Half-life is the time in which the concentration of reactants get half of its original value. So the half-life for the reaction is constant. First half-life was 500 seconds, and the second half-life is also 500 seconds, almost 500 seconds. So that means this is a first order reaction, because if a reaction has constant half-life, that means it is first order reaction, right? Now the next part is explain why a large excess of ammonia needs to be used in order to obtain the results in figure 5.3. Why we used a large excess of ammonia? To make the concentration of ammonia almost constant. Like in most of the experiments, when you want to observe the rate of reaction with respect to any one of the reactant, you make the other reactant, you add the other reactant in large amount so that its concentration is almost constant, or with respect to that particular reactant which we have taken in large excess, the reaction is zero order. Means changing the concentration of that reactant does not affect the rate of reaction because it is in large excess, right? So why we've added ammonia in large excess? So that the concentration of ammonia is nearly constant and it does not affect the rate, does not affects rate of reaction, right? And then the next part is the student measures the effect of changing the concentration of ammonia on the rate of reaction 2. Now he's changing the concentration of ammonia as well. So table 5.1 shows the results obtained, right? So he did 2 experiments. In experiment 1, they have given us the concentration of chloropropanoiodine and ammonia and the initial rate of reaction. So use the information in table 5.1 and in C2. From C2, we have calculated the order with respect to chloropropanoiodine, which is first order. Determine whether the nucleophilic substitution reaction proceeds via an SN1 or SN2 mechanism. All right, so like This is something different. This is first time I've seen it in question papers, right? The question is simple. They're just asking you about the order of reaction with respect to ammonia, but they have changed the language of the question. So this time they're asking that whether the reaction is SN1 or SN2. So now you must have an idea of SN1 and SN2 reaction as well, right? So first of all, let's just find out the rate of reaction or the order of reaction with respect to ammonia, right? So in experiment 1 and experiment 2, the concentration of chloropropanoiodine is fixed, right? And the concentration of ammonia is changing. So let's see what is the change in the concentration of ammonia. All right, so in experiment 2, the concentration is 0.00450 divided by 0.00300. So 1.5. The change in concentration is concentration of ammonia is increased by 1.5 times. So let's see what is the change in the rate of reaction. So this is 2.21 into 10 raised to power minus 5. 2.21 into 10 power minus 5, right, divided by 1.47 into 10 power minus 5. Divided by, so this is 2.21 divided by 1.47. So this is again 1.5. Powers would be cancelled out. So the rate of reaction is also increasing by 1.5 times. So that means order with respect to ammonia is also first order, right? With respect to ammonia, order is first, right? Because when the concentration of ammonia increases by 1.5 times, the rate also increases 1.5 times. So that means the rate of reaction or the rate equation, in rate equation we would have both the rate is directly proportional to concentration of chloropropanoiodine CH3 CH Cl CO2 minus and the concentration of ammonia. So because it is depending on the concentration of nucleophile, so that means it is SN2 mechanism. So like in SN1 mechanism, the concentration of the nucleophile does not matters because it occurs in two stages. In first step, the bond between halogen and carbon breaks and then nucleophile attacks. In SN2 mechanism, nucleophile attacks, and due to the attack of nucleophile, the bond between carbon and halogen breaks. So because in this reaction, the rate is dependent on both the concentration of the chloropropanoiodine and it also depends on the concentration of ammonia. So that means this is an SN2, the reaction is happening through SN2 mechanism because the rate depends on the concentration of nucleophile. All right. If it comes out zero order, that means it is SN1 mechanism. Now, the next part is describe the effect of an increase in temperature on the rate of reaction of chloropropanoiodine and ammonia. Explain your answer. So, on increasing the temperature, the rate of reaction will increase. The rate of reaction will increase. Rate of reaction will increase because the average kinetic energy of particles will increase and more particles with energy greater than activation energy. So more effective collisions will take place. More effective collisions, right? So rate of reaction will increase. Simple question. We have to describe the effect of temperature on the rate of reaction. All right. Now the next part is this is the last part of this question. When an excess of chloropropanoiodine is used, further substitution reactions occur. When an excess of chloropropanoiodine, previously they were using ammonia in excess, and now we are using chloropropanoiodine in excess. So further substitutions take place. One product has the formula C6H9NO4 2-, suggests the structure of C6H9NO4 2-. So basically we are reacting chloropropanoiodine CH3 CHClCO2- with ammonia, and what is happening here is the substitution take place. Ammonia displaces Cl, so this becomes CH3 CHNH2 CO2-. And how ammonia act as a nucleophile? It acts as a nucleophile due to its lone pair, right? And once it removes Cl, once it removes Cl and it loses the proton, because the original molecule was NH3 and we are left with NH2. So it means it has lost one of its proton to regain its lone pair. So nitrogen has regained its lone pair. So that means it again can act as a nucleophile. And this is what they're saying, that when we use an excess of chloropropanoiodine, if we have this chloropropanoiodine in excess, so the product of this reaction 1 can act as a nucleophile, and this can further attack on the chloropropanoiodine, and this would form this structure. So let's suppose we have this CH3 CHClCO2-, and now the product of the reaction 1 will act as a nucleophile CH3 CHNH2 CO2-. So now this NH2 will attack on the carbon, which is directly attached to the chlorine. So this would be partial positive. So nitrogen, due to its lone pair, will attack on this carbon, and we get CH3 CH, and one more hydrogen would be lost from this nitrogen. So we are left with NH, C double bond O negative, and then this NH is connected to CH, CH3 C double bond O negative. So this would be the structure. And now if you count the carbon atoms, so how many carbons we have? 1 2 3 4 5 6 carbons. 3 4 5 6 7 8 9 hydrogen, and 1 nitrogen, 4 oxygen. 1 2 3 4. So I hope this is clear to everyone, right? Basically this is further substitution. Nitrogen is acting as a nucleophile in the second reaction. It again attacks on chloropropanoiodine, removes the Cl, removes the proton to regain its lone pair, and we get this structure, right? So this is the structure that we get once it loses another proton and second substitution takes place. So this is di-substituted product. This is di-substituted product, right? So you can say that this is a secondary amine because nitrogen is attached to 2 carbons. So this is a secondary amine which is formed. All right. So this is the end of this question. All right, G. So this is the last question of this paper. It is saying that lidocaine is used as an anesthetic. A synthesis of lidocaine is shown in figure 6.1, right? So this is the synthesis of lidocaine, starting with this and this, right? So the first part is W can be formed by reacting. This is W. So W can be formed by reacting hydroxyethanoic acid with an excess of CoCl2, thionyl chloride or sulfur dichloride oxide. Write an equation for this reaction. So this is a general reaction We have OH, CH2, COOH reacting with SOCl2. So we know this thing that both alcohol and acid can react with thionyl chloride. So the OH would be replaced by Cl, and we get CH2 and COCl plus sulfur dioxide plus HCl. And because both OH and acidic groups are involved, so that means 2 moles of thionyl chloride would be used. So 2 moles of sulfur dioxide and 2 moles of hydrochloric acid would be produced. So this is the structure of W. You can see this here, right? So this is the structure of W. CHCl, CH2, C double bond O, Cl, right? C double bond O, Cl, CH2, Cl. So this is the structure of W. Alright, after W and X have reacted together, an excess of sodium ethanoate is added to the reaction mixture. After W and X have reacted together, this is W and this is X. So when these two react with each other, after their reaction, when the reaction is finished, we add CH3COONA, sodium ethanoate is added in the reaction mixture. Suggest why. So why would we have added sodium ethanoate? So the answer would be to neutralize any excess acid present, right? Because W was being formed from an acid, CH2, COOH, OH. So if we have any excess acid present in this reaction mixture, we want to neutralize it. So that's why we have added the salt, right? And Na will displace the hydrogen from this acid and it will neutralize the acid, right? In addition, we have sulfur dioxide and HCl. These are acidic gases. So this can be used to neutralize these acidic byproducts as well. So the answer would be to react with any acidic product, for example, SO2 or HCl, and to remove excess H plus ions. To remove excess H plus ion. So you can write either one of them. Alright, so the next part says that the reaction of W with X, reaction 1, follows an addition-elimination mechanism. Complete the mechanism for the reaction of W with X. Include all relevant curly arrows, lone pair of electrons, charges and partial charges, and use ArNH2 to represent X. Right, so we have to draw the mechanism for this reaction when W reacts with X, and the X is a phenylamine, right? And this phenyl part, they're saying that it can be represented by Ar, and the nitrogen will act as a lone pair. So let's just draw the mechanism. So nitrogen would have a lone pair. Carbonyl group has partial charges, partial positive, partial negative. So this lone pair would attack on the partial positive carbon, due to which these electrons would be transferred to oxygen. So we would get an intermediary product, Cl. Oxygen would gain a negative charge, Cl, and nitrogen would be directly connected to NH2. This gains a positive charge due to loss of its lone pair, and this is Ar. Now the oxygen, as chlorine is a good leaving group, so oxygen would moves its negative charge to the carbon, and carbon will break its bond with the Cl. As Cl is partial negative, carbon is partial positive, so these two electrons would be taken by Cl and it releases, and this bond will break. So we get Cl minus plus OH NH2 plus air, and finally to regain its lone pair, nitrogen will lose its proton, its hydrogen as a proton. Cl will attract this proton, right? This is partial positive, so it would be lost as a proton, so deprotonation would occur and nitrogen will take back these two electrons. So final structure would be OH NH Ar Cl. right? This would be the final structure as you can see here. This is the NH group after it loses its proton, and this is the AR group, C double bond O, CH2, Cl, right? So this is the addition elimination mechanism. First, amine group attacks on the carbonyl carbon, then Cl would be eliminated, and once deprotonation occurs, we get our desired product, right? Now, the next part is C2H5 to NH, this diethylamine reacts with Y in reaction 2, right? This is Y. Let's just erase all of this. So Y will react with diethylamine, right? And explain why diethylamine can act as a nucleophile, because it has the lone pair. Nitrogen has a lone pair. Nitrogen has a lone pair available, right? So as nitrogen has a lone pair available, that's why it can act as a nucleophile. All right, the purity of lidocaine can be checked using thin layer chromatography. Ethyl ethanoate is used as the solvent. The RF value of X and lidocaine are given in table 6.1. Right, this is X phenylamine, and the RF values, the retention factor for X in lidocaine is given. Now the question is, identify the substances used as the mobile and stationary phases in thin layer chromatography experiment. So the mobile phase they've already given us. Mobile phase is ethyl ethanoate. Right, mobile phase is ethyl ethanoate, and stationary phase in thin layer chromatography, stationary phase is silica or Al2O3. Either we develop a gel of silica, either we form a layer of silica gel, so it would be silica SiO2. This would be the stationary phase, and mobile phase is already given in the question. This is ethyl ethanoate. So describe how an RF value can be calculated. So RF is the distance traveled by the solute. RF is the distance traveled by solute divided by distance traveled by the solvent up to the solvent front. Okay, suggest why the RF value for X is less than that for lidocaine. So the RF value of X is 0.49 and lidocaine is 0.71. So that means X is more soluble in the stationary phase. A smaller value of RF means that X is more soluble. It moves slowly. That means X is more soluble in stationary phase or silica. X is more soluble in stationary phase, or lidocaine dissolve better in mobile phase, right? So this is just one mark answer. So you can write either one of them. Okay, now the next part of the question is related to proton NMR. So proton NMR spectrum of lidocaine is shown in figure 6.2. This is the structure of proton of lidocaine, right? So, and this is the proton NMR. Now this is the table for the environment of proton and all the chemical shift for proton NMR, right? So the question is, name the splitting patterns at chemical shift 2.6 and 1.1. So 2.6 is 1, 2, 3, 4. This is a quartet. This is a quartet, and 1.1 is a triplet. So at 2.6 we have quartet, and 1.1 is triplet. All right, the relative peak area of the peaks at chemical shift 3.0, 2.3 and is 1 to 3 respectively. Right, they have given us the ratio of the chemical shift values 3.0 and 2.3 is in 1 to 3 respectively. Identify the protons in the proton NMR spectrum of lidocaine. that are responsible for the peaks at the following chemical shift values. So we have to identify the protons which are responsible for the given peak. So a chemical shift at 7.1. So 7.1 is a multiplet, right? And this multiplet would be, it is a common multiplet. This is because we have an aromatic ring present in our structure. So this must be the protons attached to the aromatic ring. HAR range is 6 to 9.0 and we get a multiplet. So that means at 7.1 is the protons attached to aromatic ring, right? And then 3.0, at 3.0 we have a singlet, right? So 3.0 is a singlet, and so which proton can give us a singlet? First of all, this proton has no, basically the splitting pattern is due to the number of hydrogen atoms attached to the next carbon atom. So this CH2, it has a nitrogen and a carbonyl group on its left and right side. So that means this would give a singlet. So this is a singlet in our structure, and the next singlet is this CH3, which is directly attached to ring, these CH3 groups. So these two would also give a singlet, right? So there are total 6 protons in the CH3. We have 2 CH3, this one CH3 and this other CH3. So in total there are 6 hydrogen atoms. And this CH2, this has 2 hydrogens, so 2 hydrogens, so the ratio is 3:1. And this is what they have told us here, that 3 and 2.3 is in 1:3 ratio. So the peak at 3, that means the peak at 3 is due to, the peak at 3, this is due to 1:3 ratio. So that means the peak at 3 is due to CH2. The protons or the CH2, this is directly attached to carbonyl group. So let's look at the alkyl next to carbonyl group, range is 2.2 to 3. Yes, so this would be the protons, because it also justifies the ratio as well. And then the peak at 2.3, the 2.3, it is again a singlet, and it is in 1:3 ratio with the peak at 3.0. So this would be the alkyl directly attached to ring. So alkyl next to aromatic ring, this is 2.3 to 3.0, and we have a peak at 2.3. All right, so we have obtained both our peaks. So the peak at 3.0, now in solving of this question, we have used both the ratios and the values from the data booklet, from the table, right? So the peak at 3.0 is due to alkyl next to carbonyl group, right? And the peak at 2.3 is alkyl next to aromatic ring. So alkyl next to carbonyl group has 2 hydrogens, and alkyl next to aromatic ring has 6 hydrogens. So they are in the ratio of 1:3, right? The same ratio they have given us. All right, and the last part of the question is predict the number of peaks in the C13 NMR spectrum of lidocaine, right? If we have the C13 NMR spectrum of lidocaine, how many peaks would we get? So let's count the peaks, but first we have to erase all of this. All right, so the number of peaks on a C13 carbon 13 NMR. So we have 2 ethyl groups. So both of them would have same environment. So that means 2 peaks for these 2 ethyl groups, CH3, CH2. Then 3, 4, 5, 6. These 2 would give the same peaks. These 2 would give the same peaks. So 6. These 2 are same. 7. And these 2 are same. 8 and 9. So in total we have 9 peaks on a C13 NMR. 9 peaks. So this is the last part, and this is end of the paper, right? So we have solved the whole paper, and if you have any questions you can ask in the comment section. All right, take care. Allah Hafiz.